Okay, so for this video, we're going to talk about the first property of Laplace transform, which is called as the linear property. So basically, it's going to be a bunch of theorem that we are going to use for like cases that is not what we have seen before. So if you remember, what we have seen before is something like this, for which we have an individual cases. There's only one term: Laplace of tan, Laplace of t, Laplace of cos 2t, Laplace of unit step function of t minus 2. So there's only one individual term in there. Right, so what happens is that when you have like a bunch of function being linear combined together with plus or minuses, or if it's a product between couple of functions together, so automatically, so there's got to be a certain theorems that you have to use in order to find the Laplace transform. So that is why, so what we're going to do next is we're going to have a look at a bunch of properties, and the first one is going to be the easiest one that we're going to have a look at, so which is called as the linear property. So according to the property, so the definition, if alpha and beta are constants, and if you Laplace the function f of t is going to equal f of s, and the Laplace of g of t is going to equal some function g of s, then if you were to Laplace two functions, and the first one is going to be alpha f of t, and the second function is going to be beta g of t, and these two functions can either be combined by plus or minus. So the outcome is going to be alpha f of s plus minus beta g of s, so where alpha and beta are constants. So basically what is this theorem is telling you is that, right, so let's say if I have a function of Laplace alpha f of t, so plus or a minus function of beta g of t, and I wanted to find the Laplace transform of this combination of functions right here. So according to the linearity theorem, so whenever you have a plus or a minus between the function, so what you can do is you can separate them. So this can actually be written as Laplace of alpha f of t, so plus or minus Laplace of beta g of t. So you can separate them. So that is going to be the first property of linear. Alright, so the second property is that, so whenever you have a constant, so this is our alpha and this is our beta, so remember when we have an integration, so what we can do is, for example, if I have integration of 3t dt, so I can write this as 3 integration of t dt, so instead of like leaving the 3 right there, so I can bring that to the front. So that will be the same idea for Laplace transform as well. So when you have a constant at the front, so you can actually move the constant as well. So instead of leaving my alpha and beta right here, I'm going to bring that to the front of the function. So now this is going to equal alpha Laplace of f of t and plus minus beta Laplace of g of t. Okay, and according to what we have at the top right here, when you Laplace a function f of t, it become a new function, capital F of s, and plus minus beta, you just copy it down, the constants, and when you Laplace g of t, it's going to become a new function, g of s. So that is the linear property. So basically it's telling you two things. So the first thing is that, I'll put over here, so whenever you have a function that is combined by plus or minus, you can separate them. That is the first property. And the second property is that whenever you have a constant, you can bring that to the front instead of leaving that with the function that you're going to Laplace. It's going to make things easier for us. Okay, those are the two properties. That's how do we apply such property. So when you come across something like this, so here I have three functions being combined together by plus or minus. Now let's start solving the first example. I'm going to find the Laplace of this combination of function 5 exponential t plus pi cos of t minus 4t squared. First of all, let's separate them individually. So I'm going to end up with Laplace of 5 exponential of t. So I don't need that anymore. I'm going to separate them. Plus Laplace of pi cos of t and minus Laplace of 4t squared. Again, I would like to stress this to you. So the fact that this property is only applicable when you have plus or minus. When you have a product, there's no such thing. So that doesn't work. It's going to be something else, not the linear property if it's a product. Okay, so next what I'm going to do is I'm going to move the constant to the front. So here I have a constant of 5. This one is a constant of pi. Pi is a constant value. If you use your calculator for that, you'll get a value of 3.142 and something at the back, right? So basically it's just a number. So that is a pi. and the same goes for 4 as well, so that will be brought to the front. So now this can be written as 5 Laplace of exponential of t plus pi Laplace of cos of t, and then I'm going to have minus 4 Laplace of t squared. So therefore now when I Laplace this, exponential of t is going to be 1 over s minus 1, and the middle term, copy down the pi, cos of t according to the table is going to equal s over s squared plus 1 squared, so that's a 1, and then I'm going to have minus 4 multiplied by here, my n value is equal to, so I'm going to have 2 factorial over s to the power of 2 plus 1. And if I were to simplify this, I'll end up with 5 over s minus 1 plus pi s over s squared plus 1 minus 2 factorial is equal to, I'll end up with 8 over s to the power of 3. So that is going to be Laplace of the following function, right? So that will be the first example. Okay, the second example, so the idea is going to be pretty much similar as well, but here I have a trigonometric function, so I'm going to find the Laplace of cos squared t. So this is actually very similar to previous exam question. If I'm not mistaken, it's from semester 1 1920, so you can check for that. So it's not going to be exactly the same, but it probably is going to be very similar to that. So you come across Laplace of cos squared t, but the problem is that when we refer back to the table, so there's no such thing as function that is cos to the power of 2. So we have cos of a t, but that is not cos squared, so it's completely different. Okay, so it's basically a cos multiplied by another cos, not just the cos individually. So therefore, so it's not something that we can actually just come out from the table, Laplace table itself. Right, so therefore, when you come across something like this, for which it's a trigonometric function and the form is not a table, automatically what you have to do is you have to use the trigonometric property, find something that is related to cos square, but whatever that you change it into is something that you can easily Laplace transform by using the table. For example here, so we actually have a trigonometric property that states that if you have cos of 2t, so that is going to equal to cos squared t minus 1. So that will be the property. So if you notice over here, so what happens is that this is the function that we wanted to find. Can we Laplace cos of 2t? Definitely, so that's in the table. Can I Laplace a constant 1? Yes, as well, so that's actually in the table. So now all we have to do is rearrange this. So I'm going to write that. So basically cos square of t, so that is going to equal, so I'm going to move 1 to the other side. So that will be cos of 2t plus 1. And now I have to get rid of the 2. When I bring 2 to the side, it's going to be 1 over 2. So cos of 2t plus 1. Right, so that is going to be my function cos squared t. Okay, so if I have a look at this form over here, so I can simply Laplace this by using the linearity theorem or linearity property. So Laplace of cos squared t, when I apply the linearity theorem, is simply going to be the Laplace of 1 over 2, so cos of 2t plus 1 over 2. So I expand the bracket, the 1 over 2, I just multiplied each of this individually to make it easier for us. And then I'm going to apply linearity theorem. So I'm going to bring the constant to the front. For the first term, I'm going to have a half Laplace of cos 2t. So that will be the first term. And for the second term, it's simply going to be Laplace of 1 over 2. So this is just a constant by itself. There's no need to bring it to the front. Even if I were to bring it to the front, then I'm simply going to have Laplace of 1, but there's no point of doing so. You don't need to do that. Just leave the constant by itself right there. It's fine. Right, so now I'm going to Laplace this. So for the first term, when we use the table Laplace of cos 2t, my a value is going to equal 2. So that will be s over s squared plus 2 squared. So which is going to equal 4 plus, and Laplace of 1 over 2 is going to be 1 over 2 multiply, that is going to be 1 over 2 over s, which is the same as 1 over 2 over s. Let me put it there, then we'll simplify it together. And this is going to be s over 2 multiplied by s squared plus 4. And this term right here is going to be 1 over 2s. So that is going to be the outcome when you Laplace cos squared t. Okay. And again, so these are going to be my 2 examples. So when you go back to the notes that I have prepared for you, that I've given together with this, the Laplace transform right here. So you will find a bunch of examples that you can try. So I have 3 right here, and try each of them, and I've given the solution as well underneath, so you can check whether you're doing it right or not. Right, so good luck with that. I hope so this is beneficial for you for the introduction of Laplace